Well, good morning, everyone, or good afternoon, or evening, wherever you happen to be. It's a pleasure to be here. Thank you, Marone, for the invitation to talk, for the invitation to join you. Distinguished administrator. That I'm not sure is a title I ever aspired to in my career, but it's great to be here. And as Todd mentioned, CHCC is a crown jewel for the College of Letters and Science, and I've been happy to provide support for those efforts over the years, and it's a remarkable history. And so I think my job here this morning is hopefully to inspire you all with a sense of discoveries to come. And I think discoveries that will necessarily need to be enabled by the type of computing, that type of ecosystem that Marone was talking about just a few minutes ago. So I'm going to begin with, and I'll preface this by saying I come to this talk both as the dean of the college, but also as a radio astronomer, and also as a member of the board of Associated Universities Incorporated. I'll talk a bit more about that in a second. But I want to begin with this image, and Marone gave a hint of this. What you see there on the right is an image of the black hole in the center of our Milky Way galaxy. And that image was made possible by the work of H.T. Condor. And so that is a remarkable discovery. It's the third such black hole that has been imaged in this way by the Event Horizon Telescope. The other two are in much more distant, much more massive galaxies. Our Milky Way has a relatively modest central black hole, only a few million times the mass of the sun. Right. So that's the image you're seeing here on the right. On the left is a radio wavelength image of the center of the galaxy. So you can sort of see where this resides. And that blue there is the intensity and radio wavelengths of emission coming from the center of the galaxy. Now, I'm going to go do a little bit of history here. This gentleman, you might know who this is? Very, very, very dapper. It's a fellow by the name of Carl Jansky. And he was a graduate of this fine institution about 1928 or so. I don't remember the exact year. But he was a physics major, did a little electrical engineering while he was here, and left Madison to take a job with Bell Labs. And part of his responsibility with Bell Labs was to understand the source of noise in some of the early transatlantic communications that Bell Labs was interested in. And over the course of a few years, Carl Jansky determined and isolated the source of noise. So first it was recognizing that the noise seemed to be seasonal. And then it was pinpointing it onto a particular location on the sky. And it turns out that he identified that the primary source of noise that they were worried about at the time actually was coming from the constellation Sagittarius. And at the time, in the early 1900s, astronomers were very much aware that there was something special going on in the direction of the constellation Sagittarius. There's just lots of gas and dust, lots of star clouds. And it turns out that what Carl Jansky discovered was radio emission coming from the center of the galaxy. So that previous image, which is sort of what we have here in 2022, was what Carl Jansky had discovered. And in his way, he began radio astronomy and has gone on to the unit of measurement of intensity in radio astronomy is the Jansky. And it turns out that the Very Large Array Radio Telescope was renamed a few years ago as the Carl Jansky Very Large Array in honor of Carl Jansky's work. And as I say, a great Wisconsin alum. So that's sort of the beginning of radio astronomy. So I'm going to skip over about a century of radio astronomy and talk about what is coming next. And this is courtesy from Tony Beasley, who's the director of the National Radio Astronomy Observatory. What you may or may not appreciate is that over the past century, radio astronomy has grown from something that was actually done in sort of cornfields in Illinois for a while. Big single dishes were built and created over time. And then in the 1960s, a group of universities got together, recognizing that no single university could build a radio telescope that was needed to advance science, and that the national government needed to be involved in that. And a bunch of universities got themselves together and created Associated Universities Incorporated, AUI. And it became the management agency for the National Radio Astronomy Observatory. And so AUI actually has the contract from the National Science Foundation to operate the National Radio Astronomy Observatory. NRAO is headquartered in Charlottesville, Virginia, with facilities in West Virginia, the Green Bank Telescope, a facility in New Mexico, the Carl Jansky Very Large Array, and I'll show you a couple pictures of the Very Long Baseline Array, as well as the Atacama Large Millimeter Array in northern Chile. Astronomers are also greedy. We are never satisfied with the toys that we have, and so we always want more. And more usually means bigger, means more complex, and it means more expensive. And it is always driven by the science, right? The science demands more sensitivity, more resolution, the ability to map large chunks of the sky at the same time. And so that is always pushing the boundaries. Astronomy, is particularly radio astronomy, is a very technology-driven discipline that advances are needed or driven by the technology that we have. So what you see on the screen here is an artist's conception of what will be the next generation Very Large Array. For those of you that are unfamiliar with the Very Large Array, if you've ever seen the movie Contact, the second half of that movie was filmed at the VLA in New Mexico. It has 27 dishes, each of which is 25 meters in diameter, spread out over the plains of San Augustine, just west of a little town called Socorro, New Mexico. It's a great place to visit if you're ever in that part of the country. I recommend it. But what we are in now in an era of where the next generation of science is going to come from demands more sensitivity, and it demands higher spectral resolution than the VLA can provide. And it also demands sensitivity in a particular chunk of the spectrum that neither the VLA nor ALMA can achieve. And we call it this sort of thermal imaging on milli-arcsecond scales. So what does that mean? So what we are looking to build in the next generation Very Large Array, and this is sort of the technical stuff, is an instrument that will cover a huge chunk of spectrum. From about 1 gigahertz all the way out to 116 gigahertz. There'll probably be about 6 different bands that cover that range of spectrum. You can't do it all at once. But remember, we're also slicing that chunk of wavelength into tiny increments in order to be able to do the spectral line work that is going to be necessary. The wonderful thing about interferometry, and that is the basis of radio astronomy, the ability to have many, many individual detectors, each of which is collecting signal. And then that signal is combined to create an image of the sky through the magic of Fourier transforms. That means that you can keep building a bigger and bigger telescope. It also means that you have lots of flexibility in the telescope that you are building. And so what we have here is the idea is to do several different arrays that will all make up one telescope, each of which is driven by a particular science case. The one is the main array, which is 214 18-meter dishes. I mentioned the VLA is 25-meter dishes. There's a sweet spot from a mechanical engineering perspective of creating a dish that you can control, that you can point accurately, but that is also robust. There's a short baseline array, 19 6-meter dishes that are going to be very, very close together, and that allows you to have a large field of view of the sky. And so you use this to get as I mentioned, that large field of view. And then a long baseline array, 30 18-meter dishes spread out across the continental United States. And the idea there is that the longer my baseline, the higher my resolution. And so if my dishes are well separated, I can get really spectacular spatial resolution on the sky. The Event Horizon Telescope that created the images of black holes is actually a telescope that spans the globe, which is sort of the longest baseline that we can get without putting something into orbit. And there are thoughts about putting something into orbit. And then the idea is to have this be a last for at least 20 years and create a lot of science-ready data products. So one of the things, and that's I think where H.T. Condor plays a role in this work. One of the things that sort of haunted radio astronomy for a long time is that in order to do the imaging, it sort of requires, being in the club. You got to understand the Fourier transforms and the nuances of doing this. The goal of NRAO moving forward is to create science-ready data products so anybody can access the science that's coming out of one of these telescopes. So here's a sense of the scale of this thing. There's the main array, which will be centered in New Mexico, where the VLA currently is. It will then spread out into Mexico, Texas, Arizona, and then let's see, is there a laser pointer on this? These dots here are components of the very long baseline array, which already exists, but there's only 10 dishes. Your sensitivity goes as the number of dishes that you have, total collecting area. And so while the very long baseline array provides a wonderful spatial resolution, its sensitivity is not great. So the idea behind the NGVLA is to create enough dishes to get the kind of sensitivity on those long baselines that we need to do fantastic science. So that's a sense of where it's going to be. So you can imagine this is a construction challenge to put all these dishes down in various places. Many of these places are quite isolated. There are, rights of way. You got to lay enough cable. You've got to have fiber. All of those things that go into building something like this. Not to mention a contractor that can crank out about 250 dishes in a reasonable amount of time. So that's what the NGVLA will look like, spread out over the southwestern part of the country, but dipping also, as I mentioned, into Mexico. So the short baseline array, as I say, is going to be very compact, and that is the idea to give us a large field of view on the sky and sensitivity to very diffuse emission. The wonderful thing about interferometry is if you can sample all of the spatial scales, because you've got multiple baselines, enough baselines, then you can recreate an accurate image of the sky. Right. The fidelity of that image of the sky you get is really dependent upon, are you sampling as many spatial scales as possible, right? And that is the trick behind this particular short baseline array, is to make sure we can sample the very short baselines, which are the very large spatial scales on the sky. And so you can get large diffuse emission from objects on the sky with an array like this. There's just little details of the dishes. Lots of work goes into creating these things. They're very similar to dishes that are currently being constructed in South Africa for the South African radio observatory called Meerkat. All right. And then the front end, the signals, comes from these cryogenic dewars that will be in each disk, providing sensitivity across that spectral range from about, again, 1 gigahertz out to about 116 gigahertz in order to be able to give us the kind of sensitivity that we need. So each one of these is going to be receiving signals, and then we'll be able to combine those signals from all those different telescopes in order to be able to create that image or to create a spectrum of the sky. Right? So that's the secret sauce that's going to go into creating the next generation very large array. Again, massive engineering project, and one that is going to take a while. This may be the kind of diagram that you all like to see in terms of the flow of information and the flow of data. And what you can see is it is not straightforward. Right? There are lots of inputs into an online subsystem that correlates all of the data from all of the dishes in a number of different ways, and then puts that eventually out into the users out here who are using a telescope, who may be using an archive, who may be doing large projects, the staff. There's a proposal management system that goes into figuring out how to configure this in order to be able to do the science that the astronomers want to be able to do. So there's a lot of processing going in. And this is just the overall scheme of the flow of information from, as I mentioned, 250 or so different antennas, each looking presumably at the same object at the same time. But each of those signals now needs to be correlated in the way that's sort of highlighted here. So it's a complex process to do the kind of interferometry that we want to do with the NGVLA. So why do this? What is the motivation? And this is the fun part. The neat thing about this plot, which is a number of the high priority instruments that the astronautical community is moving forward, is I think H.G. Condor is involved in a number of these already. We have Ice Cube down here on the bottom. Where's the EHT? EHT's on here somewhere, I thought. CMB-S4. Yep. Which ones did I also miss something else? Yeah. But those are some of the ones. So this is the timeline from 2022, kind of where we are out to 2050, and the idea of creating these things. So the NGVLA will fully come online sometime in the middle of the next decade. So between here and there's a lot of construction that needs to be done. But astronomers are somewhat organized in the sense that every 10 years, the astronautical community gets together to try to figure out what its top priorities are, to make a request to the federal government to fund those top priorities. And that's what the Decadal Survey is all about, this document. And so this is Astro 2020, which lays out priorities for the 2020s, but also well into the 2030s. The two top priorities that came out of that were these large optical telescopes, which will be ground-based facilities, probably 30 meters in diameter, as well as the NGVLA. CMB-S4 was part of that as well. It's mapping the cosmic microwave background. So there is this process by which we prioritize the instruments that we want to have for the upcoming decade. All right, there's a science book if you are interested in getting into what is the science these crazy astronomers are up to. There is a doorstop known as a science book that you can have. And it's got a lot of great science cases for this facility. And so that's really neat. Now, a lot of work went into creating that science book. It really is a doorstop. I mean, this thing showed up in my mailbox one day. I'm like, what the heck is that? It's the science book for the NGVLA. All right, so one of the things that we're really, really interested in doing is imaging the formation of planets. Over the past, I would say, 15 years, astronomy has moved from really knowing and understanding one solar system, the one that we happen to live in, to now knowing something about over 1,000 different planetary systems in our own galaxy. So we can detect the presence of planets around other stars. That is now becoming fairly commonplace. Through those detection methods, we have some idea of the mass of the planets orbiting the star. You have some idea about where they are, how far away from that other star those planets happen to be. So the next step is to be able to detect the individual planets themselves. Right? We're not there yet. We can detect the presence of the planets and deduce certain characteristics, but being able to directly detect a planet is sort of a next huge step. One place where we might be able to do this with something like the NGVLA is in the early phases of planet formation within a planetary system. Planets form out of a disk around a star, and as that material coalesces and builds up into a planet, the thermal emission from that process for a planet particularly the size of Jupiter is bright enough to be detected by a telescope like the NGVLA. And so the idea is to be able to use this to map and image nearby planetary systems where you can begin to see the structure of the disk and the actual newly formed planet itself. And so that is one of the big key projects that the NGVLA will do. And that drives the need for that frequency coverage, because that thermal emission will peak somewhere close to 100 gigahertz. And so that's the sweet spot for being able to detect planets in formation around other stars, particularly solar system type analogs. So that'll be fun to have a catalog, a set of these forming planets to really understand what happens when a planetary system forms. One of the other things that is really great about this part of the spectrum is the richness of the molecular lines that can be detected with sufficient sensitivity and resolution. Right, so each one of the vertical lines that you see on this, and this is for the frequency in megahertz from about 24, a little less than 24,500 out to 27,500. And each one of those vertical features is the spectral signature of a molecule. And this has been one of the discoveries of radio astronomy over the past, say, 50 years, is the increasing our understanding of just how rich the interstellar medium is in molecules, some of which are quite familiar to us. So you see a number of these up here, a number of things that are actually amino acids, or at least the precursor to complex biological molecules. We see those in the interstellar medium. And the idea behind the NGVLA is to be able to probe and detect, catalog, and understand where all these molecules are and the conditions in which they are forming. Because when ultimately we want to address that ultimate question of life in the universe, or at least in our galaxy, understanding the molecular signals, understanding where those molecules are, how they are interacting, understanding what that chemistry is going to be critical to answering that question. And that's what the NGVLA will be able to do. And
looks like a mass spec.
Yes.
It's like a huge mass.
It is essentially a huge mass spec. Yes, because each one of those molecules has a number of spectral signatures that we're finding. And this, it may be hard to discern from this image, is that as we take that 1 to 116 gigahertz of spectrum, we need to be able to look at it with the kind of resolution, the spectral resolution, to be able to discern one spectral line from the next. And so that adds that degree of complexity to the signal processing and how you process that data in order to be able to get a spectrum like this from a telescope like the NGVLA. So this type of work is spawning a new type of science, and we here at UW-Madison have a cluster hire in the origins of life, and really pleased to say for the first time, I think, in the history of the university, we will have faculty who have appointments in chemistry and astronomy, who both do observational science to be able to look at spectral lines like this, as well as laboratory organic chemistry to understand how molecules interact with each other under different conditions. So a really remarkable new discipline that is emerging from our ability to be able to identify and trace molecules in a number of different conditions. And so if I were to go back an image, what you can then imagine us being able to do is to take an image like this of a planetary system that's forming, do spectroscopy on that, and understand where the molecules are, what are the conditions of the molecular material there, and where might be the raw materials for life in a planetary system that looks like this. So really on the cusp of doing some really, really interesting things. Now, something a little more near and dear to the work that I have done over my career is understanding at sort of a larger scale, when we think about a galaxy, how stars form in the first place. What are the processes that drive the collapse of clouds of gas into regions of star formation, and understanding what is going on there. What you see here are a couple of images. The blue image is from the VLA survey of a nearby spiral galaxy called NGC 628. And what you see there is sort of the optical extent of the galaxy. And one thing we realized about 30 years ago is that the gas in a galaxy, neutral hydrogen gas, tends to extend well beyond the visible part of the galaxy. The visible part of the galaxy is here. The gas content of the galaxy stretches that far out. So there's this enormous reservoir of gas out of which the galaxy can make stars. And what I generally oversimplify and tell people that a galaxy is just a machine that turns gas into stars. And our questions are, where is the gas? What drives that process of converting the gas into stars? What role might the environment play in driving that? And then what quenches the galaxy? What processes turn off star formation, largely by eliminating the gas content for galaxy? So what NGVLA will be able to do, because of that combination of sensitivity and spatial resolution, be able to image clouds of gas in nearby galaxies with exquisite resolution, to be able to get down to the actual clouds, the so-called giant electric clouds that are forming stars, to understand what's going on in that process, while simultaneously being able to image the full extent of that gas. And so this points out when I was a postdoc at the Very Large Array back in the, as you call it, the black and white days, in order to get an image like this, we had to take the VLA and do a mosaic, which means we took the array, we pointed here, 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 and then made some very large grid that may have been 10 by 10, 20 by 20. It took forever. The beauty of that compact array that I showed you on a few slides before is that you can simultaneously get this full extent of the emission while you're also getting the high resolution observations of the inner part of the galaxy needed to be able to do different types of science. So the efficiency goes way up. And we also want to know black holes in this era of multi-messenger astrophysics, which is a nice phrase that helps us recognize that our information about the universe and what's going on in the universe is not simply electromagnetic. Astronomy began as an optical science, right? Using our eyes just to look at the night sky. That evolved into how could we be more quantitative about that? Things like photographic plates and other devices that simply measured optical radiation. Over time, beginning in the middle part of the last century, we branched out, launching rockets that allowed us to look at ultraviolet radiation or X-ray radiation, then gamma rays, and then also looking at radio and near infrared, et cetera. Multi-messenger is telling us that there are other ways of looking at the universe. It could be something like IceCube, which is looking at particles and using those particles to talk about astrophysical phenomena. But also more recently, it's the gravitational waves, that recognition from Einstein, that essentially as two black holes orbit around one another, or really any two compact massive objects are in orbit around one another, they are generating gravitational waves. And if we can detect those gravitational waves and measure their amplitude, we can begin to understand what are the masses of those two things that are orbiting around one another in order to be able to learn something about black holes. Radio astronomy can detect how matter around those black holes is sort of being accreted onto those black holes and how that matter is being energized by that gravitational wave process. And that's what we can detect, to be able to understand this formation of the kind of black holes that give us the results that LIGO has detected over the past 5 years of merging black holes throughout cosmic time. Right? And so that is going to be an important field of study for the NGVLA as well. All right. So to give you a sense, I hope I've whetted your appetite a little bit about the science that will come from NGVLA. It will be extraordinary. It started in around 2000 with a number of proposals that slowly built up over the next decade to end up where we are now, where the NGVLA was actually endorsed in Astro 2020. Our colleagues in Canada are on board, busy building collaborations with other international partners. There's money from NSF to fund the prototype of some of the dishes. This is going to be a nearly $1 billion telescope. So it's a little bit of money. And that's why we actually have international partners that come along to make this possible. And so here we are, submitted this response to Astro 2020 in 2019, led by NRAO to put this together. That book, the system reference design, all the work that goes into planning a facility like this. It takes a lot of people into doing a lot of different work. It's not just science, but also the engineering and the computing that goes into understanding how to deliver a telescope like the NGVLA. Lots of places are involved in that. And here's the timeline. We hope to transition to full scientific operations, as I say, by the middle of the next decade. The NRAO is busy now of having a dish prototype that looks like it will meet the specs. And the question is, can we build enough of those, do all the cabling, lay the groundwork for that in order to be able to deliver this instrument in its full capacity by the middle of the next decade. Again, one of the neat things about an interferometer is that you can begin doing science early. You don't need the full array to start doing science. Our colleagues who build optical telescopes, you got to get all the mirrors there before you actually start doing science. With an NGVLA, we'll be able to do science relatively early. All right, and that's again, there's a sense of the timeline moving forward. And I want to skip to one of the other neat things it will be able to do is actually a bit of defense work. There are applications to the dark side, as it were, with a number of things. Because it's so sensitive, a radar can be detecting an object out there. That signal will reflect off that radar, and the NGVLA can detect that signal, no matter what it is, whether it is another satellite, whether it's an incoming asteroid. Any of those things can be done with something like the NGVLA. All right, I'm going to finish with one more aspect of the work that we have been doing, and in collaboration with a number of folks in the room. And this is a budding collaboration that we have between UW-Madison, the National Radio Astronomy Observatory, and a consortium of historically Black colleges and universities and other minority serving institutions. It's a project called Radial. And this is from one of the early Radial meetings with a number of students who were trying to understand sort of their place. And the idea behind Radial is to broaden the community, not just of individuals who are engaged in radio astronomy, but also of individuals who are engaged in the computing that goes into doing the great kind of science that we have. And so working with Lauren, Brian, we put together a proposal. Ultimately, the proposal itself wasn't successful, but we laid the groundwork for a partnership with a number of these institutions. And that partnership is alive and well. And so we will have on campus this summer about a half a dozen undergraduate students from members of the Radial Consortium who will be on campus doing summer research. And so we're in the early days, but again, the goal there is to broaden participation in the kind of work that we are doing to a community that has not been at the table historically in these endeavors, particularly from some of these small institutions. So stay tuned for more of that, and we will be advancing that as the years go forward. And with that, I'll wrap up. Thank you all for listening, and happy to take any questions you have.